What's up, guys? It's your boy Avisito. This is Leetcode 3577. Count the number of computer unlocking permutations. So yeah, you're given an array complexity of length n, and there's n locked computers in a room labeled 0 to n minus 1, each with its own unique password. The password of computer I has a complexity I, right? So the password of the computer with label I, right, is going to have this complexity in this array. And yeah, note that the first index in here by this logic is going to be decrypted already, or it's just going to be unlocked, right? And then you need to unlock all the other computers in the array following the info here, where you can decrypt the password of computer I using password for computer J, such that J is an integer less than I and complexity of J is less than complexity of I. And to decrypt the password for computer I, you must have already unlocked the computer J such that J is less than I. So basically, it needs to follow this inequality, and the computer here already needs to be unlocked, right? That's all it is. And the goal here is to find the number of permutations of this array that is a valid order of which the computers can be unlocked, starting from computer 0 as the only initially unlocked one. And you need to return modulo 10 to 9 plus 7, and that's why I have this here, right? And actually, that's why I did all these modular multiply. But yeah, look, I'll just say one thing. I saw permutations, and I implemented an MPR function, but this isn't even really needed. I'll go into that later. And I mean, I guess they also went over, the password for computer, but I mean, they already mentioned this in the problem, right? So I guess, yeah, I will let you know what I was thinking, but I mean, these are some examples, but here's one thing I want to highlight, right, from this example. So let me just write something out like that. We got 3, 3, 4. I'm just gonna do a simplified version of it. So you can order, right? You know that this is decrypted, right? This is already decrypted. Like, it's unlocked, right? So you need to try and unlock these guys. Notice that no matter what, you're never gonna be able to decrypt this, right? Because notice the following. There is no number that in this array, there's no index behind index 1. There's no index such that this guy, right? There's no index before this guy where the complexity is less than 3, right? And therefore, there's no possible ordering you can do, because this computer will always be unlocked, or this computer will always be locked. So in examples like these, you can't really do anything, right? And actually, that brings me to my next point, is that I'm going to generalize what I was saying earlier. A1 all the way to AN, right? And so we're just going to suppose A0 isn't the minimum element of the array, right? Suppose it's not. Then let min of the array be equal to a k does not equal 0. Note the following. There's going to be no possible way that you can unlock this a of k. There's no possible way, because this is the minimum, so there is no number that can, where is it? There's nothing that's going to be able to follow this. There's just nothing, right? Because there's no unlocked there's no unlocked stuff before it that is going to be less, right? There's no unlocked stuff with a lesser label that is going to have less complexity because it's the minimum complexity. That's what the minimum is by definition. It's the bottom, right? And so therefore, you're never going to be able to unlock this computer. So you're not going to be able to unlock. There's not going to be any single permutation such that you can. Oh, wait, this should be n-1. I'm sorry about that. But there's not going to be any single permutation you can do such that you can unlock all computers because you're never going to be able to unlock AK, right? So that's why you need to check first, okay, is there a complexity such that, is there a complexity that isn't 0, right? Is there any complexity that is less than your complexity is 0, right? If there is less than or equal to, if there's a complexity of I less than or equal to complexity of 0, then the number of permutations 0. There's no way you can make a valid order. And that brings me to my next point, right? And it's this. Theoretically, if you have, you must have your complexity is 0 to being your minimum, right? So A0, A1, sorry, that was a very scuffed, right? This must be your minimum. This is going to be min of your array, right? And there's no such number that's less than or equal to it. So therefore, every number in the array is going to solve, it's going to satisfy this right here. When you use, you can use computer 0 to unlock every single thing because computer 0 is already unlocked. So you can literally just unlock everything regardless of however you order these guys. It doesn't matter how you order them, right? It doesn't matter because you can always just use computer 0 to unlock everything because computer 0 has a less complexity and has a lesser index than all of these, right? This, because we already solved this case, right? And this is when this is the minimum, right? And so therefore, the way it becomes a problem of how many ways can you order this, right? How many ways can you order n-1 elements, right? Oh, sorry. How many ways can you order n-1 elements? Well, let's do that, right? Number of ways to order n-1 elements is just going to be n-1 factorial, right? And now I'm not going to go over this, but note that my solution is this is equal to n-1 factorial because of the NPR formula, which is, that's just the NPR formula. That this is going to be equal to n-1 factorial, and I took the modulus of it. And one more thing that I want to state, but that's the logic of the solution. Let me state something that I had to do, and that was that I had to make this long because I don't know if I was doing something wrong, but I kept getting an overflow when this wasn't a long, right? I just had this is an integer, this is an integer, and this is an integer. I kept getting overflows. So therefore, I just made this long, and then it just cast to an int. But I had to make it long. If not, it would cause an overflow. Actually, let me test that real quick. We just do this. Int. This is gonna be int, and I think it will give an overflow. Let me just do this as well. Oh, oops. And I'm just gonna submit it, and let's see. We'll give it overflow. It gives an overflow. So you need to make sure that whenever you're doing this modular multiplication with this factor, you have to have that long because, or it might even work with long. I don't know. I didn't test it, But yeah, you just need to make that long one. That's small point. But yeah, thank you guys for watching and keep doing your leak code and all that. And yeah,